that in mind, I'd like to change the topic a little bit and talk about earthquakes and how they equate into this whole picture and mosaic that we've been drawing today of these exponentiating feedbacks. Earthquakes is actually in there. Did you know that the earthquake rate was actually trending upwards? In this graph between 1935 and 2015, although erratic, you can see again the familiar polynomial trend line of the increasing earthquake activity that we are experiencing here on Earth. Most notably, you can see here there was a really high uptick at the end of 2004, and I believe that had something to do with that earthquake that caused the devastation in Indonesia. So take a look at this. Pretty interesting. This is 1 week's worth of earthquake, May 9th to May 15th. And what we see here is there are a lot of them. And not all of them are like small, right? Some of them are larger. We've got a 6.8 up here in Japan. That's a little bit worrying. That looks like it's almost near the Fukushima Daiichi plant. But in any case, what we can know for sure is this. The ring of fire shown here is shaking violently, and earthquake activity is on the increase. In fact, if you exponentiate out the polynomial trend line for earthquake activity, you can see that we are clearly on a polynomial trend line for earthquake activity. And you can tell, too, by looking at this, that the earthquake activity experienced by humans will at least double by 2027. Of course, it's gonna be very targeted, but it will double. Now, all this ice that's melting up in the Arctic, in particular the ice that's melting in Greenland and the deglaciation that's happening along the Greenland ice sheet, is having a very marked effect. In fact, Greenland as an island is becoming lighter, and as it becomes lighter, the edge of the island lifts up a little bit because it doesn't have as much weight. And of course, as the lip of the continent here begins to lift up a little bit, what does it affect but the actual earthquake fault that runs through Iceland, between Svalbard, and right through the center of the Arctic Ocean. This is called isostatic rebound. As melting of the Greenland ice sheet speeds up, isostatic rebound could cause earthquakes around Greenland to become stronger and occur more frequently. Earthquakes in this region are very worrying as they can destabilize hydrates contained in the sediment under the seafloor of the Arctic Ocean. As well, one earthquake can trigger further earthquakes, especially at location close by on the same fault line. So earthquakes in Greenland are very, very worrying, and I will tell you why. When you have earthquakes around that area where you have a lot of methane hydrates lodged into the soil, you get methane hydrate destabilization. So say, for example, you have an earthquake along this area. All of these methane hydrates that are within the sediments throughout are shifted, destabilized, jostled, woken up possibly, and this dissociates them and they begin to form flares, and a lot more methane gets into the atmosphere when you have earthquakes in the Arctic for this reason. They can also cause landslides under the ocean. So if you have an earthquake, you can get a whole landslide of sediment, and that sediment can start to emit methane as well, and methane gas flares. So with that, let's take a look at Iceland and the volcanic eruptions that we've been seeing in Iceland, because what they have seen is as well that the volcanic eruptions that are currently happening and have been happening lately in Iceland could be a consequence of melting glaciers due to isostatic rebound and changes. So take a look at this. This is a volcano that happened I think 2 years ago in Iceland, Bardarbunga, and it's a seam volcano. Look at that thing. It just kind of goes on. The earth just sort of opened up and started doing this. It's amazing. We're here at such a miraculous and horrible time on earth, aren't we? So, not surprisingly, when we look at volcanoes over time, this map and chart from 1611 to the present day, we find that the volcano eruption and strength are increasing over the last several hundred years. And we also find as well, shouldn't be a big surprise to us at this point, our polynomial trend line is in place. Our volcanic activity days are also on the rise. This particular graphic from a period between 1840 and 2005, you can see the familiar polynomial trend line in place again. So volcanoes can emit lightning, and they can be incredibly beautiful when they erupt. They spew massive clouds of ashes, and they set off fireworks. This one in Chile. And so as well, we can see that when volcanoes erupt, they put a very exotic cocktail of substances into the atmosphere. They put in sulfur dioxide and all sorts of other things into the atmosphere that affect our climate in various ways. As I said, they're on the rise. In Indonesia, in July, there were 5 volcanoes that erupted simultaneously in Indonesia, shrouding the skies with dark ash and clouds. This is high drama on planet Earth. Now, volcanoes have an effect on our climate, and they actually provide a temporary cooling. So we're going to just take a look at 3 volcanoes and see how they cooled the actual temperatures of the atmosphere. So in 1960 timeframe, we had a volcano, and you can see immediately after that major volcano, there was a dampening of temperature. When this one, El Chicón, erupted, we can see again an immediate dampening of temperature. And then when we had Pinatubo erupt, we had again an immediate dampening of temperature. It's because of the sulfur dioxide that the volcanoes produce. But this is very, very temporary, and it washes out of the atmosphere in short order. Oh my goodness, isn't this one beautiful? This is Sakurajima volcano in southern Japan. It's just such a high drama, pretty volcano. Okay, so these volcanoes basically, they have an effect on the temperature, and what we can see is that over time they are actually dampening the temperature a little bit. So when you factor in all the volcanic eruptions that we've been having over the last many, many years, you can see the actual temperature increase is not a degree centigrade. It is actually 1.1. So we are well over our imaginary 2 degrees centigrade of warming at this point when you factor in the volcanic eruptions.